Hi, my name is Bo, and I'm currently a summer student at the Drinking Water Research Group in the Department of Civil and Mineral Engineering. Um, and today I'm going to be talking about drinking water treatment, more specifically, a new novel process called the advanced oxidation process in use at the same time with chlorination in drinking water. So in drinking water treatment, there are many methods that are used to purify drinking water. For example, the use of chlorination with aqueous chlorine to react against different micropollutants to disinfect and kind of purify the drinking water. There's also filtration and settling, which helps to separate the drinking water from the different microparticles from the input of the drinking water. One of the new methods that exists for drinking water treatment is what I mentioned before, the advanced oxidation process, which uses UV light, the exposure of UV lights to create these atoms and molecules called radicals, which are strong oxidizing agents that react to basically any of the molecules within drinking water and kind of decomposes it. We want to target the radicals towards the target contaminants and infectants. In terms of what I'm going to be talking about today, I'm going to be talking about a method called UV chlorine, which combines the chlorination aspect of drinking water treatment with this new novel method of advanced oxidation process. In terms of the design gap in the water industry for the UV chlorine process, many consultants, utilities, municipal regulators, the stakeholders in the water industry basically are unfamiliar with the treatment process, especially with its micropollutant removal efficiency, the amount of chlorine consumed to remove the micropollutants, the amount of disinfectant byproducts that are formed, such as haloacetic acids. We're concerned about the byproduct formation, as certain concentrations of these byproducts could be detrimental to human health, whether it be carcinogenic or negatively affecting fetal development. And also, we're looking at how much electrical energy is consumed from the usage of the UV lights. So, thus, to help bridge that gap of knowledge between the stakeholders within the water industry and the academic world who knows about the advanced oxidation process, we want to build a kinetic model that can help expose these how efficient this process is at purifying drinking water. One of the first methods that kind of got me to exposed to how to do kinetic models was with the chlorine system with the different molecules of hypochlorous acid, hypochlorite, and chloride. To simulate a kinetic model, we use different ordinary differential equations to simulate the different changes in concentrations at certain changes in time, so that when we do the whole progression of the system, we'll have these little changes in concentration that will add up numerically to plot out the entire solution. And this entire we scaled it. The professor that I'm working under, he scaled it down for me just to get used to it, basically. Afterwards, another model that we designed was the inorganic carbonate system within drinking water. This one being carbonate, bicarbonate, and carbonic acid. We used the ODE solver in MATLAB and Python to test the capabilities of both languages to use as a backend for the kinetic model when we finally publish it for the different stakeholders to use. In terms of the model. So in terms of the results, as shown in figure 5, both the left chart and the right chart are very similar in terms of results. So we knew that using Python and MATLAB would be good regardless of which language that we chose. So that kind of helped us move on to our next step, which is as we added on more different kinetic equations to increase the comprehensiveness of the model, we encountered a problem of singularity, which is a problem that basically halts our progression of the model because of the fact that certain variables, as it progresses, basically escapes the relative different errors of the kind of way to contain the model basically, and allow kind of sorry yeah, give me a sec. But basically kind of it increases to like positive and negative infinity, which halts the progression of the model and accuracy of the model. One temporary band-aid solution we had to have the model progress towards the end was to decrease the relative tolerance of error, but which, although allowed the progression of the model to come from beginning to end, it was not very accurate, as seen in figure 7, where it was kind of concaving up and concaving down, and etc. To kind of remove that problem, we basically went through the model and removed the different kinetic equations and ordinary differential equations that were affecting the model and causing singularity. And through like tedious debugging, we got our model to basically progress in a similar fashion as the figures that were mentioned that I've shown before in figure 3 and figure 5. In terms of the next steps of the model, we want to increase the comprehensiveness again for the stakeholders within the water industry by adding more different species within the model, such as the chlorine and nitrate species. And we hopefully one day want to use the current model as a backend, as a web application to simulate the entire drinking water treatment process with UV chlorine for local stakeholders. And so in conclusion and the implication of this entire project, we hope that this kinetic model, as it becomes more comprehensive and it gets published to the public as a free simulator without the need of access to MATLAB or knowledge of MATLAB, we hope that UV chlorine we hope that this kind of helps make UV chlorine a more feasible option in terms of drinking water treatment, whether it be in economic feasibility, safety, and effectiveness in killing target contaminants. Yeah.
So thank you both for your presentation. Now I would once again like to address the judges and ask you guys to please unmute and ask your question.
I'll start. Nice presentation and really cool work. So if you go back to your poster, you have multiple, for your last part, the bromate has like 3 different trends depending on the settings in your solver. Mm-hmm. So which one is right? Which one is the correct one?
This one. The first one reached singularity, and it doesn't approach an equilibrium as most simulations supposed to do, like the previous figures in figure 3 and figure 5, by like decreasing the tolerance to prevent singularity. While we do kind of reach like equilibrium near the end, it doesn't like accurately model everything in a similar fashion as figure 8, figure 3, and figure 5. Yeah.
Okay, so like experimentally observed or observed in real system, it should be the right hand side one where it just approaches equilibrium.
Yeah, exactly.
At some time.
Yeah, cool. at some time. Yeah.
Thanks.
I'll go next. Thanks for a great presentation. Really good work.
Oh, sure.
I was wondering where you came up with your rate constants that you used for your calculations, and if you explored how in different environments those rate constants might change or become a function of time themselves.
Okay, so the one thing we had to keep in mind, so the rate constants were found in different literature. Like the reason why I didn't like include the references would be the fact that there'll be there's like 300 different ordinary differential equations that we're currently using in the model. So there will be like a lot of references to include for the different rate constants. But yeah, yes, the rate constants is kind of affected by time, the different pH and different like concentration within the system. But we kind of just stuck to a numerical value that was found within the different literatures for a certain pH we're trying to like model within, which is usually around 5 to 8 pH ranges of 5 to 8.
Thanks.